electronegativity values. They ranges from 0.7 to 4.0. So here these values which are here under each of the element is the electronegativity value. Okay, so it's starting from 0.7 to 4. So if you take francium and cesium, they have the electronegativity value of 0.7, which is the lowest. And then if you take fluorine, it has the higher electronegativity values, that is 4.0, right? So if you have a general observation on this table, the electronegativity values have a general tendency to increase from left to right in the table, right? There you see 1.0, 1.5, 2.0, 2.5, 3, 3.5, 4, right? So they have a general tendency to increase from left to right across the table, right? But the difference need not to be equal, right? Since the first group, first column, first row, it is 0.5 increasing, but it is not mandatory to increase by 0.5, right? So here if you take the second one, it is 0.9, 1.2, that is 0.3, right? So the general tendency, it is increasing across the table from left to right. Also from top to bottom, it is decreasing, right? 1.0, 0.9, 0.8, 0.8. So it is decreasing. So here you see 1.5, 1.2, 1.0, 1.0, 0.9, 0.9, it is decreasing. So this is just a general tendency. Okay. And if you take the second row also, 0.9, 1.2, 1.5, 1.8, 2.1, 2.5, like that, right? It's increasing. This row also, if you see, it is increasing. So 1.3, 1.5, 1.6, 1.8, 1.9, it's increasing. So there are certain instances, this 1.5 and 1.6, certain instances, they will be decreasing. So there can be several reasons for that, right? So this is what I'm saying is the usual phenomena, right? Towards the down of the table, electronegativity values will be decreasing. From left to right, electronegativity values will be increasing. So these elements with less electronegativity value, we will call them as, in other way, electropositive elements, right? Electropositive elements. So that's what I show in the previous slide. So here you see electropositive elements, right? So if the electronegativity values are less, then we call them as electropositive elements. And if the electronegativity values are high, then we call it as electronegative elements. Okay. So these electropositive elements readily give up electrons to become plus ions, right? So these two will have the tendency to give away the electrons and will become positive ion, right? And these electronegative elements readily acquire electrons to become negative ions. So electropositive elements will give up electrons and electronegative elements will receive those electrons. So you just need to know the tendency. So what is happening down the table, what is happening across the table from left to right, right to left, right? So if you see here in these two particular boxes, right, I told you, right? So this box in between barium and hafnium, right? So here is our barium and here is the hafnium in between them, and after radium, right? So these two tables are the F blocks elements, right? These are the F block elements. Usually that will be written at the bottom of the table separately, right? Otherwise the table would be very big, right? So here already 18 columns are there, 2 here, 10 here, and 6 here, 18. If you write these 14 also here, then the number of column would be 32, right? Then that would be so big. So that's why we take all of them out and write them in the bottom of the table separately. And those all are like high radiative elements and difficult to find in nature. Difficult to find, I say, with radioactive elements, these all are in this F block, right? So this is our electronegativity values. And why do we need these electronegativity values is to determine whether the bond is covalent or ionic. If it is ionic bond, how much of percentage ionic bond is that? Will it be stable, right? So will it gain electron or lose electron? Will the bond formed is stable? Which element can form another bond? So if you have, so we have one chlorine, but there is a sodium and a potassium. So what is would be the scenario? Potassium will form because if you see the electronegativity values, K is 0.8 and sodium is 0.9, but chlorine it does have the 3. Where's our chlorine? Okay, 3.0, right? So the difference between chlorine and sodium is 2.1. Okay, the electronegativity value difference is 2.1. But in the case of K and Cl, K has 0.8 and Cl has 3.0. There we have 2.2, right? The electronegativity value is 2.2. So which means this potassium is highly electropositive, not highly, okay, a little bit electropositive than sodium, right? So this one has the tendency to connect with the chlorine fast, right? So if I put cesium also in this column, right, cesium also, then the difference would be 2.3. Then cesium has the highest tendency to bond with the chlorine, right? So what I'm saying now are all usual phenomena. There are exceptional situations, right? So this is why we need the electronegativity values. So based on this, we have a separate table also, right? Which that table will show us which elements can react with which elements, right? So if I have NaCl, right, if I want to separate this Na and Cl, right, then I will go for K. So what will that K do? K will react with Cl and remove this Na alone, right? So this is why we need the electronegativity values, right? This is why we need the electronegativity values.